I think 2 weeks or so, kind of we've tried to delve a little bit into the foundations of large language models. We had some preliminary discussion, sorry, me highlighting pages as I usually do when I'm reading things online. Yeah, we had some pretty much discussions on the basic foundations, tokenization, position encoding, pre-training recipes, distributed learning, scaling laws. And then today we'll probably just discuss scaling laws and mixture of experts. I'll try to have this completed within the next 20 minutes or so, or 30 or so that Derek can introduce us into fine-tuning, which I'm really excited about. And I'm also really looking forward to the discussions on evaluations and benchmarking, because I think that's really crucial. So what are scaling laws? Scaling laws here, the fundamental principle here is how scale predicts the performance of large language models in general. So I'll discuss a little bit about the scaling laws, the foundations, how it's used in deep learning, and some of the one very important principle here, the chinchilla scaling principles. I will discuss a little bit about that. Have some some papers that I've looked at. We might have a chance to review some of those eventually. Then I'll talk about some of the beta lessons of AI research. So, what are scaling laws? Scaling laws describe how changes in model size, the data set size, or computing power affects an AI model's performance. So they are kind of crucial or for to help us predict how well our models will perform without needing to spend extensive resources on trial and error. So it pretty much pins on model size parameters, data size, tokens. Here we're talking about large language models, not multimodal models, then compute essentially. So it allows us to make reliable predictions about model performance. So that's essentially what we talk about when we are talking about scaling laws. So scaling laws, because we measure model performance in terms of the size of a model in terms of its parameters, and the size of the data set is pretty much measured in terms of its tokens. And during the discussion we had uh, on tokenization, when we discussed the chapter on tokenization, we discussed about what they are. They are just subwords, characters, very tiny fragments or units that can be used to pretty much compress words into formats that the machine can easily understand. So the practical the meaning of power laws here is pretty much a mathematical equation that has a form y equals to bx times a, where y here could be is the performance, and then x is the scale. Then we have the slope of the curve here as as b, and then the y here is the y-intercept. So as you can see on the graph, on the log-log plot for power laws, as you increase the value of one of the parameters, the other pretty much increases in a sort of a linear fraction. So in our context, y might represent the performance, and x would represent the scale, or for instance, the number of parameters. So this is what a typical power log. When I was reviewing and preparing for this class, this presentation, I sort of reviewed some of the scaling law chapter from the book on AI safety. I believe I dropped the link in the chat, but I should still be in the chat also. But I really encourage having sort of glancing through the scaling law from the AI safety book, which I think is pretty cool. So I picked up that slide from here, which kind of projected us that linear relationship, typical linear relationship that exists. Uh, Yeah, so why does scaling laws matter? In deep learning, performance scales according to model size, as I said before. It depends on the data set size, like how many tokens the model is trained on. It depends on the compute resources. So how many flops is used during training. So as we increase these variables, the model loss typically decreases following this predictable power law patterns. But the biggest challenge or limitation often comes down to computing resources. So because computing resources is equally as important, or not so, if not probably more important than anything else. So it pretty much those are the main three parameters that go into the scaling law. So there is a phenomenal paper here that was introduced by um, Hoffman. Really encourage. Let me see if I can open the paper here. Try to open. Yes. So this is the paper, training compute by large language models. So I think in this paper they pretty much try to. Let me see if I can open this. Should have it open somewhere. Yeah. So the authors of this paper essentially were trying to make they were trying to the main hypothesis of the paper was that this is the problem they identified. They found out that that many large language models are on the train due to a focus on model scaling size without increasing the amount of data. So their hypothesis in this research essentially was that researchers proposed that for compute optimal training, both the model size and the number of training tokens should scale equally. So doubling one requires doubling the other. So this hypothesis was tested with using over 400 models in this particular research paper, and I think about 70 million to 16 billion training tokens. And what they were able to find was that the chinchilla outperformed several state-of-the-art models like Gopher, GPT-3, Megatron, etc., despite its smaller parameter size. So they pretty much were able to hypothesize that the importance of a proportional increase in the performance of a model size in terms of parameters, and also the amount of training compute that's pretty much added. So as you increase the amount of parameters, as you can see on this graph, on the figure, this graph that I'm projecting here, you pretty much have a linear increase in the amount of performance. So this was the principle that was pretty much laid out by the authors of that paper. So model size and data are important for compute budget, essentially. And smaller models with more training data can essentially outperform larger models. So that was the major point that the authors of the paper were trying to make. And I saw this image that I think Derek shared in our Slack channel, which pretty much shows again that same relationship between training loss and model size. As you can see, up to a certain point, as the model size increases, you have a transient loss in performance, and then as a sort of decrease, and then sort of increases as the model parameters increase. Why is this important? What are the implications? It's important for planning. So the ability to predict performance before training is kind of important. It helps to avoid oversized models, and also to optimize cost as well. So you're able to compute, to have the necessary compute that you need for the algorithms, or for the right amount of resources that you need for training the models. And I put a link here to the presentation that I had previously made on distributed learning. I think those were pushed on GitHub. Those were added by John on the Slack on the GitHub page. So those slides are available, including the presentation of pre-training recipes as well. I think those slides are equally available on the GitHub. I think John integrated those already. So that'll be a nice refresher to that. Scaling laws hold true across many modalities and orders of magnitude. The generative AI models typically follow the scaling laws, but are not so true for more discriminative models like image classifiers. So that's a little bit of a change there. But in general, for generative AI models, it applies, but not so much for more how do I say it? More specialized or discriminative models. The bitter lesson here is that scaling beats intricate or expert designed systems. That if you invest in compute and data rather than manual feature engineering, it's a lot better. There was this interesting article by Sutton, I believe Richard Sutton, where they pretty much made the argument that AI progress has resulted from cheaper computation, not human designed decisions based on problem specific information, because we've seen an explosion or an increase in the amount of computational resources that has been available, and I think that's what has driven the AI revolution as it is today. So that's the argument that Richard Sutton in 2022 was making in this particular article. He made the point that the reason we're able to scale is because we have more compute, but both have to go hand in hand. So more compute plus data is greater than greater than human ingenuity alone. And there've been a lot of criticisms and debates around the chinchilla principle. There's an argument that the scaling laws are not universal, and it's a very valid point for that. And the equations have also been debated, and many people argue that it's subject to refinement. So scaling laws may evolve as models and tasks become more complex. There are issues around the replication issues, the emulator. Oh, I don't know why the link to this post didn't highlight. I might have to go back and check, but there are some replication issues that were pointed out in this particular blog post, and the fact that future laws may refine predictions. What are some of the implications for AI development? It will help us, scaling laws will help for more resource allocation. So the ability to optimize ratio of model size to dataset size. It will help with investment focus. So compute is always our fundamental bottleneck. You may be aware that the XAI company has purchased, I think they have under their belt about the most GPUs probably, but I think about 200,000 GPUs from the official announcement. So there's just a huge arms race to purchase as much computational resources. I think they've kind of come to understand that it's probably the most biggest investment, I guess, best return on your buck would be to get as much resources as possible. I think that's what that race is all about. But there's been also an argument whether or not algorithmic efficiency trumps computational resources. And we've seen this argument a lot since the release of DeepSeek as well. You know, which one is more important? Algorithmic efficiency, computational resources, data, etc. So that's where kind of becomes relevant. Future capabilities may be predictable through extrapolation. AI timelines, scaling laws inform predictions about AI progress. So those are the key points there. So the power laws kind of gives us an idea of trends where future directions may go, but they are not overall universal, as several authors have pointed this out. And there's a lot of debates around the universality of scaling laws. So these are some of the resources that I looked at before for this presentation. One of them was the article by Rania Hossam, who wrote on the chinchilla laws for large language models. I think those are available in the presentation. You can look at those. We have the chinchilla um, wide implications, which I also would encourage you all to have a chance to read. Excellent, excellent resources there. The scaling laws by Clement Thierret, which I think also very helpful there for really understanding scaling laws in the context of the OpenAI GPT model. And also a video by, I think, oh, yeah, yes, another video by the ChatGPT, the Anthropic, the person behind Anthropic, the CEO of Anthropic. It's taking long to load, but he's essentially talking about scaling laws during a presentation at Stanford University. I think that's pretty much it. That's pretty much it concerning scaling laws. I just wanted to give that very brief overview of what scaling laws is. But the main key takeaway there is the importance of aligning compute with parameters, model parameters, and the importance of scaling both in synergy. But again, that's very useful for our generative large language models. They may not apply for more discriminative models like image classifiers. I think that's the main key takeaway there that I wanted us to take from there. Before I pass it on to Derek, I just wanted to quickly overview mixture of experts because I made just 2 slides on it, 3 slides on it, I think.
While we're in between the chapters, I think you might have mentioned this already, but with the scaling laws, I think the Chinchilla articles mentioned how you scale the compute and the data set size in the same way. Could you comment more on that?
Yeah, they made the point that both should go in synergy. The increasing the amount of data should go in synergy with the size of the model. So in the article that I had shared earlier, they had made I mean, essentially the chinchilla principle is pretty much attributed to this Hoffman paper. They had made the argument that as you increase the model parameters in size, you should also increase essentially should also increase the amount of computational resources. This kind of saw a linear relationship there between the model parameter size and also the amount of compute. But again, this only applies for large language models. When it comes to more specialized or discriminative models, that relationship becomes a little bit distorted. I think they had another graph somewhere where they discuss that relation. Yeah, this is one of those graphs where they discuss that relationship with essentially with different model sizes. So where you can see a slight decrease in the training, and you can see an increase a decrease in the training loss as the number of parameters pretty much increase. So I think it's a pretty great paper. I put a link to this article in the slide presentation, and I could drop it in the where's my Zoom? Where's my Zoom chat? I can drop that in the chat still. I think it's a really fantastic paper. Really great way to think about that. Thanks a lot for the question. Yeah. Last slide, I think, okay, oh, it's 5 slides. Okay, so the key thing we want to take away here is what is a mixture of experts. The idea here is to attribute just some parameters, but so you want to optimize on specialization. That's just the basic concept here. So within large language models, you want to attribute certain parameters per task, and that can help with optimization. So so that's pretty much the fundamental principle here, that if you can specialize different domains within the large language models, you need less memory, you need less compute, and you can prompt more on efficiency. So this is a nice figure I took from the internet, which pretty much shows that as you input more and more tokens, you can have more specialized expert models that are fine-tuned to handle very specific tasks, and then and that kind of helps to produce more refined results down the line. So I think that's the fundamental principle in mixture of experts. And the reason why that's important, or why that matters, is because it uses less memory and time than dense models. It helps to scale knowledge without slowing down. And an example of that is the Mistral model, and also the GPT-4 model that has been released. So I think that's pretty much it for now regarding this mixture. Oh yeah, so this is the person I was talking about, Dan Hendricks. He looks very young here, but he's not actually that young. But really great author here. He's one of the leading leads in terms of discussing about AI safety issues. I think really tremendously published there. Really encourage, if you guys have a chance to look at some of his materials. I'll drop the link again in the chat, but some of his materials on the AI fundamentals in general. With that, thanks a lot. I think I will, if there are no questions, I will pass it on to Derek.
Thank you, Bryan. Always appreciate the work that you all have been putting into this. If I go on and try to teach my own students about mixture of models, I've been trying to work on an analogy. And since I'm currently in academia, I still think about what grad school and selecting your advisor looks like. So if you're in a department, you might have multiple professors, experts that you could work with. So suppose we're talking about artificial intelligence. One professor is an expert in natural language processing, another professor is an expert in image processing, and so forth. When I think of a mixture of experts, I think of going in those routes and saying which professor I want to work with, depending on what the project I'm interested in. What the papers also said were, at some point, the expert or the professor in my analogy might be too busy, might have too many jobs or too many students to handle. So there might become a point where you have to actually have a maximum number of students per professor, and you might have to move a student to a different professor as well. So that's how the mixture of experts algorithms seem to proceed.
Yeah, yeah, that's such an excellent analogy. Thanks for that.
Okay, can you see my slide for instruct fine-tuning?
Yes, I can.
Okay. All right, folks, continuing right along with our genai handbook, we're going to move into the module for fine-tuning large language models. And time permitting, I think I'll talk about chapter 19 at the moment. Instruct fine-tuning, learning objectives, quite frankly, is to introduce fine-tuning first and then motivate what we mean by instruct in this context. And give credit where credit's due, following the resources from our GenAI handbook. I'm gathering these materials from the blog post by Sebastian Reuter, who I believe worked at Meta, and a video by Shane Longpre, who gave the talk at Google. So what do we mean by fine-tuning? What I'm envisioning is a practical world where if you're using something like a ChatGPT 4, you're going to have a large language model that has already been pre-trained somewhere else. And for most of us, we do not have the capabilities to make models nearly as large or as capable as the ones already out there. Most of us are not spending millions of dollars for the electricity and the compute time that Bryan was mentioning earlier in this session. So for practical purposes, most of us are going to use what's called a pre-trained large language model and maybe adjust it for our purposes back at our own workplace. And that's where the fine-tuning comes in. So the thought process is you have the pre-trained model and you're going to leave that quote unquote frozen. You're not going to change the weights for that. And instead, you might tweak or slightly adjust the weights here and there for your particular purpose. And that's where the fine-tuning comes in. Some thoughts on the matters for the various large language models that were out at the time. This picture is from 2022. Again, in the gray boxes on the left, we have our pre-trained language model, and we might fine-tune it towards completing a task and hopefully get the machine to understand what we mean by that task. We might fine-tune it on the way to the task, as you can see there in the top left for the BERT models. We might do just a tiny bit of prompting, such as some back and forth when you communicate with your chatbot there in the bottom left in the GPT-3 idea. And when you ask the chatbot to slightly change or update its response, in the literature, we might call this few shot prompting. And then on the right side of our diagram, if we have a more intentional workflow, we might ask our language model to handle several tasks simultaneously. And that's been coming up in a group of language models called FLAN. So now we'll go into instruct fine-tuning. To motivate this, I simply pulled up a ChatGPT session and asked the obvious question, what are quartile markdown slides? And if I phrase it like that, at the time of this recording, I'm asking for a definition. And the GPT chatbot, in my opinion, did a great job of helping me understand the topic, what are quartile markdown slides. Now, however, for the sake of today's session, what I needed was an actual task. There you can see my prompt in the top right. Please write a few slides about instruct fine-tuning in quartile markdown. So this time around, in an earlier version of GPT and other chatbots, the response would have still been only definitions. It would have tried to define words like quartile and markdown. Because the more recent chatbots have been trained to help us with tasks, like in my case here, making quartile markdown slides, now it's already been instructed to give me a response in the correct format, and that's namely the quartile markdown. Instead of only defining quartile markdown, it's actually giving me results in quartile markdown. Remarkably, thanks to its training data, it's also giving me the YAML at the top of the script file as well. So again, results like this are available to us because people, or perhaps an additional AI, have instructed the chatbot in recent years to refine the answers to be able to carry out the task that we request of it. From the Google talk, I appreciated simplifying the jargon a bit. We could, for our purposes, perhaps equate the notions of alignment tuning and instruction tuning. And this opens up what we can have our AI chatbots do for us, such as open-ended task, creative generation. And what I'm really optimistic about in the near future is the need for human feedback. There may be some pessimism that artificial intelligence is maybe taking over too many of our job functions. But as technologies change, we may be creating a new type of job function where we are asking humans, perhaps experts in some fields, to give human feedback to some of this. This has come up in notions such as prompt engineering. And I believe next week we will combine some ideas to talk about RLHF, reinforcement learning with human feedback. So I'm actually wondering in the near future if human feedback will become more and more in demand as these technologies grow. I'll have a few examples in the upcoming slides, but just to give an overview, when we instruct the AI, when we instruct the chatbot, there may be different ways where we could provide our human input. One of them is called mixing a few shot settings. That is just maybe providing a sentence, 2, 3, 4, 5 of extra prompting. We could help our chatbot become robust by working it through some tasks diversity. As you saw in my earlier examples, in addition to producing Quarto Markdown, it also produced the YAML at the top of the page as well. And at least for the data science programmer, those were two different tasks that often go together, and the AI knew to handle that simultaneously. Third bullet point, we could have the AI go through data augmentation. And one example of that is turning a question answering task into a question generation task. And then finally, the notion of mixing weights. If you feel that some of your training data is underrepresented for what you're trying to do, you might change the weights of how this proceeds through your AI architecture, so that way the underrepresented training data is no longer underrepresented. Now, going through some of the recent papers in instruct fine-tuning. In creating questions, the researchers had human volunteers try to create structures like this, where there was an input, output, and reason. And this is coming from a lab and paper by Mishra and their team back in 2022. For an example, a positive example, input sentence, Jack played basketball after school, after which he was very tired. The output, how long did Jack play basketball? That is to say, we want to show the AI an example of an appropriate conversational question that would naturally follow up the input. The reasoning is also provided by the human to the robot. The question asks about the duration of an event, Therefore, it is a temporal event duration question. Now, in the bottom, a negative example, the sentence being, he spent 2 hours on his homework. A possible response is, how long did he do his homework? However, this is a negative example by the reasoning that we do not want this question as an answer, since the question was already answered. It was already something that was provided in the input. So because that question, how long did he do his homework, is not asking or creating more information, we're going to call this a negative example, especially in the notions of reinforcement learning. Now, a couple of examples of answer generations. We'll start with a positive example at the top. The idea in education is a simple fill in the blank type of quiz. So that's what we mean by trying to find a context word that fits the prompt. The input question, the trophy doesn't fit into the brown suitcase because blank is too large. As we discussed back in the sections about attention, when you have a pronoun or you need to have, in this case, the blank, refer to something in the sentence, usually a noun that came beforehand. Grammatically, that blank might be trophy, that blank might be suitcase. Here, the human is providing a reasonable example that the word trophy fills in that blank. And furthermore, because of the spatial relationship, we need that the large object has to be inside the other one, in this case of the trophy and the suitcase. In the bottom example, virtually the same setup, trophy, suitcase, blank. What if, for example, a machine drew a completely different noun, like bottle? We note that the reason is that bottle is not one of the objects present, trophy, suitcase. So a valid answer must be one of the objects presented in the question. Once again, these were, to the best of my knowledge, employed humans that were brought in to create positive and negative examples like this to fine-tune a large language model with these question and answer generation tasks. For this particular slide, there were 8 items. I simply created a GT table to get everything on one slide. Otherwise, no intention was to structure otherwise. The next year, Honovic et al. In 2023 talked about more broad situations that we could have in language generation, in text generation. And this is now under a branch of instruct fine-tuning called unnatural instructions. Because for those proponents of GPT and other chatbots, we point out how much these chatbots can do, in addition to some of the questions and answers from before. Some of the newer capabilities for chatbots include experiment verification, recipe correction, such as recipes for cooking food, character categorization, talking about perhaps characters in a fiction book, characters in maybe a role-playing game campaign, poem generation, idiom explanation, very useful for people learning a new language, trying to learn a subtle customs, author classification. If you're looking at old text that might not automatically be attributed to a particular person, you might be able to go back and by their written cadence, figure out who was responsible for writing that document. Word invention, and quite frankly, humor understanding. If you are in a situation where you want to understand a joke or meme or so forth. Now, at the time, newer chatbots, we might try to push things along with exemplars. And admittedly, for my book club here, I did not understand this as much. In the left column, we have without chain of thought processing. In the right column, we have chain of thought processing. Top row, we have instructional input without exemplars. And bottom row, we have instructional input with exemplars. So notice in the top left, if we ask it a simple question, can you write a whole haiku? It just says yes. In the top right, can you write a whole haiku, but we want the reasoning as well. So the chatbot will respond with, I know what a haiku is. It has this structure, and I do have the capability of writing a haiku. In the bottom left, without chain of thought, we could have a question like, could a dandelion suffer from hepatitis? Yes or no? In the bottom right, we want a chain of thought as well. Could a dandelion suffer from hepatitis? And the chatbot's going through its literature materials and answers with some reasoning. Hepatitis only affects organisms with livers. Dandelions don't have a liver. By logic, the answer is no. So when we're fine-tuning AI with question and answer generations like this, the researcher, the analyst, might want to consider how you deploy these exemplars and also hoping that you could verify the work being done by seeking out chain of thought responses from the AI chatbot. When we talk about language models, we usually talk about how they've been trained on large corpuses, such as all the Wikipedia articles or many Reddit posts or all back issues of the Wall Street Journal. When we talk about image processing, in order to get many more thousands of images, we might have mentioned how the training data is augmented by taking the images and slightly adjusting them, moving them left, right, up, down by a few pixels, maybe flipping the images vertically, horizontally, maybe doing a slight rotation, um, maybe slightly changing the colors, but maintaining the aspects of the image, like, oh, it's a picture of a dog or a cat, for example. With the same train of thought, when we talk about fine-tuning with instructions, we might want to take some of this human intervention and provide thousands of additional inputs. And in order to do that, as you can see on the present slide, the strategy might be to use what's called input inversion, where we have these questions, answers, and train of thoughts, but we could also have this flow through the AI architecture in any of those permutations. And that's at the time one of the current ideas in fine-tuning our AI chatbots is to improve the task diversity with input inversion. So those are my slides for instruct fine-tuning. Let me welcome any comments from my colleagues here in the book club.
It seems like on the augmented part, it was kind of grammatically incorrect. So maybe it was missing an article before the explanations. Maybe in that paper they may have made a mistake. Yeah, right here. Because bottle is too large. Maybe they meant to say the bottle, but maybe the system has a way to add the article. I would assume.
Yes, there probably were some issues that would come up between natural speech and also these volunteers were I didn't show the top half of the image or what the human volunteers were told to do, but there were reasons for the brevity. So what we'll go into next week is now when we're talking about these large language models, which already, as you saw earlier in the session, have millions, if not billions of parameters. And these at first would have a lot of compute time and a lot of real world expenses. What we'll look at next time is to try to combat these notions with perhaps um, dimensionality reduction and some other ideas in lieu of the scaling laws and some of the pressures we have in having larger and larger models.